First of all, thank you, Xanadu, for inviting me again to QHack. I'm quite excited. So today, I'll be talking about a pretty recent project. In fact, the paper came out yesterday on where a bunch of colleagues at Zapata and I worked on a project where we call this reliable ground state preparation on early fault-tolerant quantum computers. Yes. Um, And so first, I want to go through or review variational quantum algorithms, specifically the idea of VQE and QAOA, the variational quantum eigensolver, or the QAOA being two early examples, or in fact, the first two examples of variational quantum algorithms. And they really inspired a family of variational quantum algorithms, including a lot of the near-term methods in quantum machine learning. Specifically today, I'd like to focus a bit more on VQE, where the main task at hand is to prepare the ground state of a Hamiltonian or to estimate the ground state energy. And so to give a brief review of VQE, VQE is a hybrid quantum classical algorithm. And according to the left figure, on the quantum computer, you prepare a quantum state of interest using some sort of parameterized quantum circuit or an ansatz. And by estimating expectation value or values using measurement outcomes from your quantum computer, you feed this data into the classical optimizer to update the parameters of your parameterized quantum circuit. And in a scheme like VQE, the choice of the parameterized circuit or the ansatz, as well as the classical optimization of these parameters, have been shown to be crucial to the performance of the algorithm. And so what do these ansatz actually look like? And so in fields like quantum chemistry or applications like quantum chemistry, you have something like the unitary coupled cluster circuit, which are usually more physically motivated. In more near-term applications, or more recent applications rather, like quantum machine learning, or you're trying to run some proof of principle experiments on near-term devices, you often have circuits like the ones on the right, where you have some sort of multi-layered circuit structure, and you're populating it with some hardware-efficient gates. And so specifically, a lot of these multi-layered circuits have this unit cell or a circuit layer to them, some unit or amount of circuit depth that you repeat up to some k times in the hopes of generating a more flexible circuit. And so I've been really interested in these parameterized quantum circuits for a while. And one of the main questions I more recently asked myself is will adding more circuit layers to my parameterized quantum circuit always or necessarily improve the performance of my algorithm? And the answer seems to be a little more complicated than I thought. And I want to explain this through an example. And so this is an example of a VQE calculation that was run by Zapata about 2 years ago, where the problem at hand is to estimate the ground state energy of the 1D Fermi-Hubbard model. And this plot plots the energy error on the y-axis as a function of the number of circuit layers. So they propose a particular type of parameterized quantum circuit, and they use the number of layers and plot the corresponding energy error. And this number of layers you can think of as a proxy for the circuit depth. And so in this particular plot, the performance metric that they're tracking is the energy error, and the objective is to lower the energy as much as possible up to some threshold, which is shown by the yellow solid line. And in this experiment, as well as what we often do as VQE practitioners, we add more circuit depth in the hopes of further decreasing the energy. However, in calculations like this specifically, you do see some sort of a troubling region between layers 13 through 25 or 29, where you see that even after you add more circuit depth, there's no significant improvement in the energy. It's almost kind of plateauing. And why might this be the case? This could be one or a collection of reasons, including the proliferation of local minima or undesirable saddle points in the energy landscapes of this VQ calculation, or it could be the limited expressiveness of your parameterized ansatz itself, and or as you add on more circuit layers, this also accumulates a large number of parameters in your circuit. And this can lead to a difficulty in optimization in the vast parameter space. And so to summarize what we're seeing here, we again see that adding more circuit resources, such as the circuit depth, does not necessarily lead to improved performance. And another way of saying that, or at least the term that we started using, is the fact that VQE or VQ-like algorithms can be quite unreliable. However, I also want to note that there's been lots of really exciting progress trying to deal with or improve upon this unreliability of VQE. One of the very recent examples being Nathan's work, as well as Roland at Xanadu, trying to with developing a new method for optimizing deep quantum circuits. And so I thought it's worth highlighting that even though this seems to be a major issue of VQE, there's lots of work going into improving upon it. And so to go back to this idea of reliability, I wanted to make sure I define this a little better, where ideally, we'd like to get our money's worth with quantum circuits. That is, if we were to pump in or add in more circuit depth, we'd like to see or observe better performance in return. And in the specific case of the ground state preparation problem, we wanted to find if there are such reliable circuits. And in this task of ground state preparation, the performance metric that we're interested in is the ground state overlap or the energy. And I note that in order to develop such algorithm where if you see this circuit depth, you see this reliable conversion to improvement in performance, we note that these types of algorithms or methods are probably not well suited for near-term quantum computers or NISQ devices where the depth requirements are quite strict. Instead, where we believe such reliable methods to shine are these early fault-tolerant quantum computers, where we assume some amount of error correction, which essentially allows us more circuit depth to kind of play with in our algorithm development. And so going back to the reliability in quantum algorithms or circuits for the specific task of ground state preparation, I wanted to kind of motivate this by posing a possible scenario. And so suppose you have optimized your VQE ansatz for a particular problem, shown in blue here, and you track the progress using this energy versus the circuit depth or the number of layers plot, much like the one that I showed you earlier with the Fermi-Hubbard model. And you see that first the energy seems to plummet, and then it seems to saturate or plateau at about a suboptimal value that's above some sort of accuracy threshold. Maybe for quantum chemistry, this could refer to the chemical accuracy threshold. And so given this scenario, you run this optimization many times and you see this consistent type of observation. What can you do with this VQE optimized circuit? Was this a waste? And the answer is it might not be so, especially if we can add some sort of operation on top of this VQE optimized circuit that now provides reliable improvement. So if you're willing to add in some amount of that, you're pretty much guaranteed an improvement in the energy or the ground state overlap. And so given this some sort of mystery operation, which operation would actually ensure this? And so one potential realization of such operation is, at least for the task of ground state preparation, some type of operation that will increase the ground state overlap while decreasing the overlaps with other eigenstates. And a potential operation that accomplishes this would be a function of the Hamiltonian that decreases with energy. So I'll explain this a little in a couple of slides, but in this work, we call such realization of this function a ground state booster. And so for the rest of my talk, I'll be giving you a high-level overview of these ground state boosters. First, for what is a booster / what does it do? And so suppose you have an input state. This could be some easy to prepare mean field state or some VQE optimized state. And you can express this in terms of the eigenstates of the Hamiltonian. And so if we ask ourselves, what happens when you apply a function of the Hamiltonian to this input state psi, what you see according to this equation below is that you're effectively reweighing the contributions or overlaps of each eigenstate. And given this, what specific properties should this function f have such that the contribution or the overlap with the ground state is boosted or increased while contributions of other eigenstates are decreased? And again, the answer is if f is monotonically decreasing in energy, we can achieve this property. And so to describe this in a more visual fashion, I thought about given some input state psi, plotting the overlaps with each eigenstate ordered in the magnitude of the eigenvalues. And so suppose your input state looks something like this. You have some ground state overlap that's shown on the left, as well as overlaps with other eigenstates. And suppose now that you apply some sort of monotonically decreasing function of the Hamiltonian f to this input state. And so again, as I mentioned a couple of slides back, what this does, the effect of applying f is that you're reweighing these overlaps. And essentially, you see that once these bars are normalized, effectively, after this action of f, you see that the ground state overlap is boosted while the overlaps with higher energy eigenstates are suppressed. And by looking at this type of picture, you could also gain another type of observation or property of f, in that if f were unitary, this would only add phases, meaning that the heights of the bars will not be able to be changed. However, because the whole point of f is to boost the ground state overlap, meaning boosting the bar height for the ground state and lower the bar heights for the other eigenstates, this implies that f would need to be a non-unitary operation. And so keep this in mind when we go over how we would actually implement f on a quantum computer. And so, right, as I mentioned before, now that we have some idea of what a booster does, how do we actually implement a booster on the quantum computer? And so we note that the f of h, the function of the Hamiltonian, can have a Fourier decomposition in the following manner, where you see that this is essentially a linear combination of unitary matrices, where each of these basis elements is a unitary matrix. And to show a simple example of such Fourier decomposition, we consider the example of a cosine booster, which only has two terms in the linear combination of unitaries. And so for this particular example, how do we implement such linear combination of unitaries on an actual quantum computer? And it turns out that there's a method that is called linear combination of unitaries, or the LCU method, that you can use to apply f or cosine of AH to some input state psi. And it's in the following, where for this particular example, you'd only need one ancilla qubit that you'd have to prepare in such a way that it encodes the coefficients in the linear combination. Then this is followed by applications of these controlled time evolution operations. So U here would correspond to e to the IAH, and V corresponds to e to the minus IAH, followed by some unpreparation of the ancilla qubit, and you measure. And if the measurement outcome is 0, then you know that you've applied the right linear combination of unitaries on your input state psi up to some normalization. And here, using this circuit picture, we can clearly see that f is a probabilistic implementation. It's conditioned on the outcome, measurement outcome on the ancilla qubit. And now that we know how to actually implement a booster probabilistically on the quantum computer, one might ask, well, what actually makes a good booster? what are some good properties or characteristics. And I note that this is somewhat of a balancing act. And so we want the booster function to satisfy or balance the following mathematical properties. So in the paper, we go over some mathematical properties, but for the sake of this presentation, I also pair it with a more high-level interpretation of what this mathematical statement implies. For example, if F is monotonically decreasing in energy, this corresponds to the ability to boost overlaps with low energy eigenstates, while suppressing the overlaps with higher energy eigenstates. And if the Fourier coefficients of F decay very rapidly, this allows for a low depth circuit implementation of that particular booster. And lastly, if the function itself, F, decays rapidly, this implies a better capability of suppressing overlaps with the higher energy eigenstates. And so this is a lot of facts thrown at you, but for this talk, I wanted to also provide an example of what a good booster is. And as an example, we call this the Gaussian booster. And so for this Gaussian booster, I write the ideal booster function form here, where you have a parameter called A, which controls the width of your Gaussian. And while I skip over a lot of the technical details here, in our work, we essentially tune A according to some objective function that we proposed that balances the properties of a good booster that I mentioned briefly in the previous slide. For more information, I encourage you guys to check out our recent archive paper. The number is here, where we provide a more general framework for designing low depth boosters. But going back to the Gaussian booster, again, the question is, how do you go from this ideal booster function form and implement this function on the quantum computer? And so in practice, what you would do is compute the Fourier transform of F, and then discretize and truncate this Fourier transform. And that would yield an equation like I showed a few slides back, where you have a linear combination of unitaries. And as we've gone over with the example of the cosine booster, you can implement this probabilistically using the LCU method. So in practice, what you're doing is applying an approximate and probabilistic implementation of your booster. And so to show the capabilities of the Gaussian booster, we wanted to show some numerical simulations, specifically for preparing the ground state of the nitrogen molecule. And the performance metrics that we're going to keep track of are the ground state overlap, as well as the energy error with respect to the exact ground state energy. And what we're going to do is we're going to increase the circuit depth of the Gaussian booster and track the overlap and the energy. And just as a reminder, going back to this idea of reliability, what we would like to see in the booster method is, as we increase depth, we'd like to see some reliable conversion from providing more depth would correspond to a reliable improvement in the algorithm performance. In this case, this is either by decreasing the energy or increasing the ground state overlap. And in order to kind of have an aside where we compare the depths of the Gaussian boosters, suppose we have two Gaussian boosters, one with a larger A, or A being the width parameter, larger A, or a smaller A. And so visually, we see that larger A corresponds to a rapidly decaying booster function. And so what this implies is this larger A value implies that there is a need for higher order terms to well approximate this F booster function, which implies that you need larger maximum time in the control time evolution operations that's used in the LCU circuit. And we use this letter T to describe or represent this maximum time. And this then directly corresponds to a greater circuit depth. And just to summarize what I just said, so having a larger A in your Gaussian booster implies that you have this larger T value, which implies that you need to essentially your booster will have greater depth than if you were to implement a booster with a smaller A value. So going back to the numerical simulation then, we plot the performance metrics, the ground state overlap and the energy error as a function of this depth proxy T, the T that I described a slide back. And so we see that as T, or the depth, increases, you see this decrease in the energy, as well as this increase in the ground state overlap. And you might be asking, why does this plot look so jagged? And it's because this T actually has to do with the approximation that we make on the booster function f. Like I showed a few slides back, in practice, we can't actually implement this booster function perfectly. We need to discretize and truncate the Fourier transform. And so in this especially low T region, you're making a quite low quality approximation to the booster function, which then causes some of these points to be quite jagged and zigzaggy. And so going back to this idea of reliability of boosters, I wanted to show some qualitative difference in reliability between methods like VQE and the booster. Of course, this is not a fair apples to apples comparison because these two plots show different ground state preparation problems, but it was more for the qualitative purpose, where on the left and the VQE, this is the same plot that I showed earlier to talk about the fact that VQ can be quite unreliable. There are cases in which even if you add in more and more circuit layers, you don't see this nice conversion of depth to improvement in performance. On the other hand, for boosters, this seems to be a more reliable method in terms of converting circuit resources like the circuit depth to improved circuit performance. But then again, this is a qualitative difference, and in order to really analyze or more closely analyze the differences in reliability of these two methods, we do need further benchmarking. And also, I'd like to note that there are lots of possible booster functions out there, but not all boosters are equal. So as an example, there might be something like the exponential booster on the left or the Gaussian booster on the right, with the ideal function forms written right below. And we note that for the exponential booster, the Fourier coefficients decay quadratically fast, whereas for the Gaussian booster, the Fourier coefficients decay exponentially fast. And so what does this actually mean? So having a more rapidly decaying Fourier coefficients implies that you can truncate the Fourier decomposition of the booster function at fewer terms, and each of this term corresponds to a controlled time evolution operation in the LCU circuit. So what this implies is that given the same A value for the exponential booster and the Gaussian booster is significantly lower in circuit depth. And so put in another way, given a fixed A, the exponential booster may be better at boosting the ground state overlap, but this comes at the cost of greater circuit depth. So it really depends on, of course, the quality of your device and what type of depths your quantum device can reliably implement. But depending on that case, Gaussian booster might be a better candidate. And so tying it back to VQE, one potential application of boosters is to really augment or improve upon VQE. And so suppose you can use the VQE circuit to make a good initial guess of the ground state wave function. Then especially if your quantum device can afford extra depth, then it might be worth trying to implement some sort of low depth booster function, like the linear combination of unitary circuit that we showed earlier, in order to refine or go the last mile with the booster and get you to a state that is closer to the ground state. And so hopefully through this talk, I gave you a high-level overview of what boosters are, what it can do, how you implement it, and what is considered a good booster. And so as a summary, as a more big picture statement, there is a need for us to develop quantum circuits or algorithms that reliably improve performance, meaning there's this reliable conversion from inputting circuit resources and outputting or observing better performance. And boosters, we see it as a particular case for reliably boosting the ground state overlap for the task of ground state preparation. Specifically for Gaussian boosters, we observe that as you increase the width parameter A, or the circuit depth, the ground state overlap increases. Although we didn't go over this particular part, we note that having a larger width parameter results, or larger A parameter results in a lower success probability. But this can be improved using methods like amplitude amplification, especially if you can afford the depth. Lastly, while boosters are more reliable, they're definitely too deep to implement on near-term devices. And therefore, they may be more applicable or useful for future devices like early fault-tolerant quantum computers. And so for a couple of future directions, we'd like to incorporate effects or model of noise into the booster framework. For example, as depth of the booster increases, we expect noise to deteriorate the performance of boosters. So to more robustly analyze the performance of boosters, we think somehow adding some sort of model of noise would be useful in better understanding them. And secondly, I'm not too sure where to begin with this, but what would be really interesting is if we can think about a booster-like or similarly reliable circuitry for quantum machine learning algorithms. I haven't thought too deeply about it, but it might be hard because I believe for a lot of these quantum machine learning algorithms, there's no notion of this problem Hamiltonian. And with that, I'd like to thank my colleagues, my co-authors for this work, as well as Luis for helping me create a lot of the figures for explaining boosters. And thank you, everyone, for your attention. I'd be happy to take questions. And lastly, if you want to learn more about boosters, we encourage you to check out this archive paper that we posted yesterday. And so thank you.
Amazing. Thank you so much, Dylan. Chat, make sure to get your questions in there for Dylan. I will ask the questions on your behalf a bit later. Dylan, thanks so much for the talk. I definitely want to ask some questions on the technical side, but maybe we'll start with something a bit more light. You told us that doing science involves like creating with your brain, building things up in your brain, creating new ideas. But you're also, turns out, quite handy. You like to kind of build things with your hands, with your sweat as well. Maybe you tell us a little bit about that interest you have.
Yeah. Just like you mentioned, I feel like a lot of quantum computing work, at least for me, and not being on the hardware side, right? A lot of inventing and the creative process happens just like in our brains, and we're just thinking a lot. But I also like to kind of express my creativity and build, right, using my hands. So it could be simple as building with Legos, but also especially during COVID and quarantining, I've been learning more about home maintenance, although I don't have my own home yet. But for example, luckily my parents live nearby. So I went over to their place to help build a patio with my dad for their backyard, as well as every year around the springtime, I help my parents with restarting a veggie garden. And so every summer, what we do after building the patio is basically have our own grown veggies and have kind of host Korean barbecues on our patio, which is super rewarding.
What's your favorite dish in that Korean barbecue?
Oh man, so many, but well, I like this type of Korean barbecue called samgyeopsal, so that's definitely one of my favorites.
What's in that one?
Oh, so I think it's basically some like fatty part of pork, so that you just grill it and then you make like a lettuce wrap with like rice, the meat, and then some veggies, and it's really good.
Dylan, I do have to ask you. It sounds like you are in the immortal debate of Lego versus Legos. You are in the Legos camp. Is that true?
I think so. Oh wait, what's the argument about? Is it that
I think what is the plural of Lego?
yeah, I would say Legos, but it just sounds right. But maybe I'm missing something.
Yeah, I always called it Lego when I was a kid, both singular and plural. It's like emoji, right? What is the plural of
Oh
emoji? One of those impossible questions.
man, yeah, that's really hard. Yeah,
So for Lego, when I was a kid, I think nowadays you can get like, the Death Star Lego, like really advanced Lego sets. But I used to
yeah.
love just like throwing the whole box on the floor and just like letting my mind go wild. Do you ever do that?
Yeah, yeah. So I think my process would be like if my parents bought me a Lego set, I would like follow the instructions and make it and maybe like show it off like on some table for like a couple of days. But then I would break it and add all those pieces back into this like giant bin of Legos from like all the previous sets. And then that's where like your own creativity can really shine. I think actually that process sounds a lot like how we develop algorithms for quantum computing, right? Taking
Interesting.
pieces from other pre-existing methods and then like either putting them together or taking components of each algorithms to invent a new algorithm. Um,
So quantum computing is just like Lego, but in superposition.
exactly. That's a good way to put it.
Awesome. Dylan, you told me that in kind of a very short time, you've gone from being kind of a trainee, a student, having supervisors and mentors, so now actually taking the role of the mentor yourself. What have you
Yeah.
learned in the past little while, now kind of growing to that stage of your career?
Yeah, really great question. I think one big lesson that I learned, so when you're especially a young grad student, I think the role that you play is you like to kind of do everything yourself, like code it up, like think of, well, maybe at the development of the algorithm side, you do it with more senior folks, but then you're the one who like wants to get your hands dirty and like code it up and make all the pretty plots and simulation results. But when you're supervising, you kind of learn to let go of some of that and like trust the other person that they'll do that job really well. I think that process was a bit hard because there's a part of me that's like, oh my God, like maybe I need to code it up and I need to check it myself. And there is still an element of that, especially with like pen and paper, for example. But right, these days, I've luckily had an opportunity as Zapata to supervise an intern this past year. And it's been very rewarding to kind of like let them really take over parts of the project and let their creativity really shine and right taking a step back almost.
What have you learned in that experience that you kind of now realize that your own supervisors and mentors were doing back when you were in that stage? Have you recognized now only in hindsight what they were doing?
Yeah, yeah, I think I'm appreciating my supervisors and mentors like Alon and Peter a lot more. Yeah.
Nice. You also told me that you got really into podcasts the last couple of years. What do you like about podcasts compared to say listening to music?
Yeah, I mean, I wouldn't say I'm a huge podcast listener. I've just started checking out a few podcasts. I'm usually a pretty bad auditory learner. I need kind of like some sort of visual or text in front of me.
Hmm.
But I'm realizing now that you don't actually have to take, well, it is like really interesting when the contents of the podcast are interesting, but you don't necessarily have to take away everything from the podcast. I think I had this like notion that like, oh, like if I don't get everything that they're saying to me,
You got to
like
pay
what am I doing
attention.
with my time? Yeah, but you can, for example, like cook and listen to a podcast and just take away points that you find interesting or like so yeah, I'm really learning this like art of multitasking uh, by listening to podcasts.
Nice. Have you discovered the trick that a good podcast is actually a good way to fall asleep?
Oh, oh, actually, I think I've learned that, but I never like fully recognized it because yeah, there are times where right you're listening to a podcast and it's really interesting, but then the voice gets like too like they're like very gentle speakers and you just feel yourself falling asleep.
I think maybe it has something to do with when you're falling asleep and if you're in a quiet room, especially I don't know about you, but my brain tends to go a mile a minute, and once I have that quiet space, it tries to process everything. And if I have a podcast, it kind of shuts off that
Mhm.
that like racing part of the brain because it's now has to attend to the podcast. And that's, for me at least, a really great way to fall asleep.
Oh, yeah, that's a great point. Yeah, another way I realized for myself is I stopped working like at around like 7 or even earlier sometimes, and that just helps me sleep better because if I'm like working till 9, my brain is still moving, and that just messes up my sleep
Yeah.
consistently.
It's nice to have that transition period, have something else to take your mind off.
Agreed. I think that's one great part about actually having an industry job. You have this like set 9 to 5 uh, time versus when I was a grad student, I was yeah working at such odd hours.
Yeah. Your colleague Alejandro told me that he used to go to bed at 4:30
Oh,
4:30 a.m. during his grad student days.
that's really impressive. I don't think I've ever done that. Like maybe in undergrad, but in grad school, I think my body would just got too old for this.
Awesome. Let's jump into the science a little bit. So I'm curious
Sure.
about this notion of reliability because it seems to be kind of a like a new notion you're proposing here. Or maybe you could just
Mm.
kind of what hit upon this notion of reliability that people in the past had missed.
Yeah, I think this was actually partly inspired or rather in agreement with some talks that I heard from Maria Scholl like around last year, where she was talking about this. Uh, she was making this argument, and I'm paraphrasing her. I'm not sure if this is the actual point she was trying to make, but she was like, there is really a need to uh, design circuits or ansatz where we have a very good understanding of what that circuit is doing to a quantum state. And I think she was talking about this in the context of quantum machine learning because she was realizing these hardware efficient ansatz, we don't actually know what it's doing. We're kind of trusting the classical optimizer to do everything for us, essentially. So along those lines, we started thinking, at least for the task of ground state preparation, where it might be a little more structured than quantum machine learning, uh, is there a way to come up with some quantum circuitry that where we know we have a very good idea of what the circuit is doing, and because of that, and in addition to that, boosters, I guess, is an example that also reliably converts the circuit resources that you pump into the quantum algorithm, and you get to see this like resulting improvement in the performance. And so, yeah, I have to say, like listening to Maria talk about something similar in quantum machine learning was very encouraging. I think we're all starting to think about very similar things. And she also noted from those types of talks that likely these informed circuits or ansatz designs will come from or borrow techniques from the more fault tolerant algorithm side, where we do have like very a lot of structure in those algorithms, meaning maybe you could roughly interpret fault-tolerant algorithms as applying very specific functions on the amplitudes of the wave function, whereas in NISQ algorithms, it's this like really messy, complicated functions of sines and cosines in terms of the parameters of the quantum circuit.
For sure, I definitely think that we've gone through a few waves. Initially, it was kind of hand drawn algorithms derived by experts on the whiteboard, very exact, very specific, doing very particular things, interfering in exactly the right way. And then when
Yeah.
we had the tools of QML, we decided we don't need any of that. We're just going to throw this at some optimizer, not think at all about our structure of our circuit, and pray that it works out. And now I think we're kind of oscillating somewhere in the middle ground, right?
Yeah, exactly. But yeah, I do appreciate that a lot of the works in this NISQ era or variational algorithms really helped us identify that problem. I think so. Yeah, I think these works have been very valuable. I think without working in variational quantum algorithms for a while and thinking so much about parameterized quantum circuits, I wouldn't have gotten to think about more reliable circuit design.
For sure. And I think it's inevitable if you look at what happened in machine learning. People don't use a structureless vanilla neural network. They always have some sort of structure that it kind of matches the problem and allows you to train more efficiently or get, match a better distribution to your data.
Right, right.
Awesome, Dylan. Why don't we take some questions from the chat? I know a few of them have been coming in. I'll relay them for you. So, question from Heisenberg's dog. Can't we just use adiabatic or digitized adiabatic state preparation methods on early fault-tolerant quantum computers, or use adiabatic methods for a good initial starting point followed by VQE or QA/OA?
Yeah, that's an interesting point, and I don't actually know what the depth requirements for such adiabatic quantum computation would be, but at least in our archive paper, we did a very rough back of the envelope calculation for this N2 example, comparing the depth costs of a low depth booster like the Gaussian booster to something like phase estimation, and we saw that the depth requirements were a small fraction of what it would require on, for example, the phase estimation algorithm. But in terms of this adiabatic approach, I have to say I'm not too familiar with the depth requirements.
Fair enough. How about we take a question from user Abby from Canada. Why is the implementation of the booster function probabilistic?
It goes back to the fact that this f that we're trying to, this function of the Hamiltonian, as we saw earlier in the in this like pictorial representation, I noted that if f were unitary, this would only add phases so that you can't really actually boost the ground state overlap. So f is going to be a non-unitary operation, and in order to implement this type of operation on the quantum computer, this will have to be probabilistic, if I understood correctly. Yeah.
I think that's a good answer. Question from, let's go again to Heisenberg's dog. It says, how are T and the circuit depth related? Is the circuit depth equal to some constant times T?
Yeah, so let me go back.
See if you can pull up your slides for you here on the stream so we can see.
Yeah, so I would, so what was the question again? Sorry.
Question is, how is T is related
this?
to the circuit depth? Is the circuit depth maybe a constant times T?
Yeah, I believe I have to check back in the paper, but I believe there was some log factor, log of T or of some sort. But yeah, we just used a T as a depth proxy, but what I do agree that one of the future directions of this work is to have a more kind of a robust analysis of the depth requirements of the booster. We don't carry any robust resource estimation for this work yet. We just use T as a rough, since T essentially represents the maximum time in the time evolution of the LCU circuit, we use that as kind of the proxy for depth. But yeah, this would require a little more work in the resource estimation part.
Cool. Why don't we now take a question from Ningxi? Question is, I'm not sure whether you have it right from your presentation, but though boosters are reliable, they're too deep for NISQ devices. So how about other devices? I guess the question here, if I can paraphrase, is, if they're very deep for NISQ devices, does that depth concern still carry over to, say, fault-tolerant devices? Is it still going to lead to a long circuit?
If I understood correctly, if we have some sort of an early fault-tolerant quantum computer, it may be enough to carry out circuits of this amount of depth. It's definitely out of reach for NISQ devices. But related to that, one question I have, well, not that I want to throw a question back, is, for example, in the scheme that I had here, application of augmenting VQE, one question I have is how what VQE would look like when implemented on an early fault-tolerant quantum computer, right? Because you may have some level of error correction, and I don't know if running VQE on that type of device will be as simple as just varying the angles and directly implementing like we do on NISQ devices. So I think a little more thought has to go into what would VQE look like on these types of new devices. Um, but I think for that question that was asked, I think, yeah, we do believe that boosters are probably implementable on especially post NISC devices.
Great. I think that probably does answer the question. I am curious about, you said, on this idea of when we have an early fault tolerant quantum computer, maybe VQE looks different. Like, is VQE somehow fundamentally a NISC thing, or will still be using VQE during the fault tolerant era?
Yeah, I'm actually I don't think I have enough background on kind of error correction and fault tolerance to best to answer this question, but I have a feeling that, for example, like I'd be interested in if you were to tune the angles of some like parameterized gate, like for, or rather, if we have an early fault tolerant quantum computer, as algorithm practitioners or developers, can we just think of this computer as just a type of computer where we have more depth than a NISC device, or would implementing VQE be more involved? Thinking about, for example, oh, like there are certain like small angles that we can't reliably or robustly implement, so you would have to think about the ranges of the parameters that where this type of circuit would run well on these post-NIST devices. But yeah, I have to say I'm not too sure what VQE on post-NIST will look like. And another question is, will it even be like worth it?
For sure. Yeah, I definitely think that gathering, like one of our guests yesterday, Jared, was big on, like, as soon as you gather data from the world, it changes your idea of what you can do. And I think we won't know what we can do with a quantum computer until we have these more powerful devices and we iterate on ideas, new ideas develop because we couldn't see them until we had those devices.
Mm-hmm. Yeah, yeah.
Cool. I think it's time for one more question. I actually want to ask a question of you about, I know you've worked on the open source project OrcViz, and the idea there is to kind of visualize the optimization landscapes of variational circuits. So why is it important to work visually? Why is it important to see what you're doing rather than just throwing it at a black box?
Yeah, so this could probably be answered by like reading the OrcViz paper. It's not only kind of a paper that describes how you can run the code, but there are actually algorithm examples that my colleague Manuel nicely kind of organized. One of them, let me just give you an example where Manuel used OrcViz to compare landscapes of related QAOA or related graphs that were solved using QAOA. And you see that I think from previous works, you knew that good parameters of one QAOA problem can transfer to a QAOA problem that corresponds to a related graph structure. But we didn't really know what the exact landscapes of these two problems would look like. So Manuel used OrcViz to essentially plot a low dimensional kind of projection of these two landscapes and showed that not only are the good parameters similar, but the landscapes themselves are quite similar. And so, right, so visually looking at landscapes can sometimes provide a better understanding or further kind of advancement in your understanding of variational quantum algorithms.
Great. Dylan, that's unfortunately all the time we've had for the segment now. I really appreciated the conversation and the great talk, and we thank you so much for joining us today at QHack.
Yeah, thank you for the invitation.